This is lesson 7, exercise 5H, identity and inverse matrices. The learning goals for this one is to look into what an identity matrix is, what an identity matrix can be used for, the matrix multiplication of an n by n matrix with its respective identity matrix, also on the class pad 2, look into the determinant of a matrix, and to look into the inverse of a matrix. There's quite a few learning goals for this one. And the success criteria is to know how to find the inverse of a matrix through its determinant or through the class pad calculator. Now, admittedly, before we get started, identity and inverse matrices, without the context, a lot of the formulas are going to seem abstract, irrelevant, and almost arbitrary. I don't like teaching this content without visuals and without knowing where and why these formulas are there, where they come from and how they originated. But seeing as how we're very crunched for time, you've just got to take the formulas for what it is, for their face value. And I'll try my best to explain what formula you need to use and when to use it, depending on the type of example. For now, just bear with the theory side of it. So in ordinary arithmetic, the number 1 is called the multiplicative identity element. When 1 multiplies a number, the answer is always identical to the original number. So what this means is if I did 5 times 1, this is just saying, okay, here's what I'm multiplying by. What's one lot of what I'm multiplying by? Well, that's just going to give me the same answer. And you can apply this times 1 to any number and you will always end up getting the same answer again, depending on what you multiply with. So what we want to know is there a matrix that can multiply any other matrix, given that you now know your matrix multiplication skills? And I want to get an answer that's identical to the original matrix. So in other words, it's always going to have to be a square matrix. But if I had 3, 2, 9, 8, and I multiplied this by another matrix that we don't know, question mark, question mark, question mark, question mark, I want to be able to get the same answer as 3, 9, 2, 8. Now, provided that I already talked about this little fact here, you would think, oh yeah, that's easy. You can just put 1, 1, 1, 1. But all ones in this case will not work. You can try it out on your class pad calculator to see why it's the case. But what it is this here. And we're going to look at this example. Here's a matrix A, 5, 2, 8, 3. And this is a matrix I standing for identity. And there is a diagonal, leading diagonal, go from left to top left to bottom right, full of 1s, and the other numbers are 0s. And in fact, if we multiply this with this, we should get the same answer as the original matrix. Let's have a look. 5, 2, 8, 3, multiplied by 1, 0, 0, 1. Now, before I even consider writing the working out for this, let's just have a look at what's gonna happen. We're gonna get the first row and the first columns, the first row in the first matrix, first column in the second matrix, and this is gonna multiply with this is gonna multiply with this, and then be added together. Well, we can do that straight away in one go. 5 times 1 is just 5, and 2 times 0, well, that's gonna give me 0. So 5 plus 0 is just 5. Yeah, just similar to this here. And then we're going to do this again, but this time it's going to be this first row with the second column now. 5 times 0 plus 2 times 1. Well, 5 times 0 is 0, and 2 times 1 is 1, so 2 times 1 is 2, sorry. So 0 plus 2 is 2, which is exactly the same as what we have here. Again, 8 times 1 plus 0 times 3, that's just 8. And then again, 3. So we end up at the exact same matrix as what we did before. So 1s are involved. That was a shocking circle. 1s are involved. Let's try that again. 1s are involved. There we go, close enough. But it's just based on the leading diagonal of 1s. Now this again works if we do a multiplied by I, the matrix I rather multiplied by A, 1 0 0 1 multiplied by 5 2 8 3. This will suffice the same answer. So the order of the matrix in this case makes no difference. You'll end up with, again, 5 2 8 3. So when it comes to inverse multiplication, identity multiplication, it's commutative. We can flip them around and still get the exact same matrix that we originally intended to, provided that the matrix is a square matrix. So it's a 2 by 2 or 3 by 3 or 4 by 4. In this case, we're only going to be focusing on 2 by 2s. So the identity matrix, this is what we call it, for any 2 by 2 matrix, is just a diagonal full of 1s. And if we were to get any matrix A and multiply it with I, or that same matrix A and multiply it with I in the front, you will end up just with A to begin with. And we can prove it with this example here. So the identity matrix I also has a special property that it is commutative, as what I said before, in matrix multiplication. When I is one of the matrices in the multiplication, the answer is the same when the order of the matrices is commuted or reversed. So remember that matrix multiplication is not usually commutative. Only square matrices have this identity, identity matrices. The identity matrix for any square matrix is a square matrix of the same order, so the same size, with 1s along the diagonal, which is what I was saying before. So if I get a 2 by 2 and multiply with this, I'll get the same 2 by 2 matrix, a 3 by 3 matrix, and a 4 by 4 matrix, provided that there are 1s along the diagonal and 0s within the other positions. Now the reason why we're looking into this new identity matrix is that we are going to use this identity matrix to then figure out a thing called an inverse of a matrix. So let's say there is some type of matrix, which is A, and we have A to be 5, 3, 9, and 9. Now, if we multiply it by its identity, 1, 0, 0, 1, we get the same answer. But what I want to know is there a matrix? Is there a matrix now where we're going to look into it a little bit differently, and I'll erase that once I'm done. Is there a certain matrix that when I multiply it by whatever A is, I end up getting the answer 1, 0, 0, 1. Is there a matrix that we can put in here? Well, we can't put 1, 0, 0, 1 into here because that will give us the original matrix that we began with. We don't want this to be the answer. We want 1, 0, 0, 1. So what matrix can we put into here? Now, whatever this is being coined as A inverse. We don't know what A inverse is. We can't necessarily solve for this. There are ways or methods, but let's just put some terminology to it. Let's just call it A inverse. So only square matrices have the ability to find an inverse of a matrix, so 2 by 2, 3 by 3s, and 4 by 4s. How do we get it? And there are different ways. The first way I'm going to show you was on the ClassPad calculator. So we're going to find the inverse of 8, 4, 3, 2. Let's grab our calculator out. Alright, so go into main, get our keyboard out, math 2, and let's put in this matrix 8, 4, 3, 2. So 8, 4, 3, and 2. Establish that as matrix A. Execute that, and now we have matrix A. Now, in the textbook, it does show that you can use a small letter. You can. I just like keeping consistent and putting in a capital letter. Alright, so we've done that. Now we want to just find the inverse of this, and the calculator can do this for you. Type in A, and then go to keyboard, go back to the keyboard, and we're going to press this power button here. And all we want to do is just write it the same way as how it's been coined, what the terminology is, and it's just to the power of -1. And there's our inverse. So what is this inverse? What does this mean? This just means if I were to get this matrix here and multiply it with this matrix here using the rules for matrix multiplication, I will end up with the answer 1001. And let's find this out. Let's do A multiplied by A inverse. And I should get 1001, and that's correct. So again, it seems arbitrary. I mean, it seems kind of random. Why are we trying to find this? This will help us with the next exercise in regards to simultaneous equations, and there are real life contexts to it. The only thing that's different is that there's kind of new terminology, and there's a new process or a new visual method of showing how we can solve simultaneous equations through matrices. And this is the main reason why we look into this. Definitely will pop up in further maths. So definitely get yourself used to this process and this method. So we're going to now manually find the inverse of a 2 by 2 matrix. Just make sure this is in line. All right. So step one is to find the determinant of the matrix. Now a determinant, there's many functionality and uses for what's called the determinant. Again, there's not enough time to show you. There's a plethora of videos. I recommend looking up this guy. I'm going to show a picture of this now up on the screen. He has some really awesome maths videos that shows you the determinant and other things as well, but specifically the visual side of what a determinant does. I'll leave the link up as well here if you want to go ahead and check this video out. All right. So if we have ABCD, so ABCD within the matrix capital A, some random numbers, to find the determinant of this matrix, all we need to do is grab what A and D is, multiply it, grab what B and C is, multiply it, and these two multiplications here, we find the difference. For a matrix that have an inverse, determinant must be a non-zero answer. It could be negative, it could be positive, but it has to be non-zero. If the determinant is 0, then an inverse does not exist, and A is what's called a singular matrix. Very arbitrary and quite a random thing to say, but just bear with me. Then we're going to calculate this inverse. So once we found its determinant, to get the inverse, we have to do this crazy step, and I'll focus just specifically on this one. We're going to change a matrix that has A, B, C, and D. Remember, these can be just any random numbers. And we're going to find out the determinant, which is A times D, which I'll just write AD, minus B times C. This is our determinant of that matrix. We need to get this determinant, and then with this determinant, we're going to get its inverse by doing this. 1 over the determinant, which is AD minus BC. So we're grabbing A and D, multiplying it, getting B and C, multiplying it. This will be a scalar that's in front of the matrix. And we're going to just change the positionings and the signs of this. D and A are going to swap around. Right, so the number D that was in the initial position will now be placed here, and A, whatever this number is, will now be placed here. And B and C will still be the same, but they'll have a negative in front. And that's how we find the inverse. This is pretty much what the calculator is doing. It's grabbing these numbers, it's finding out the determinant, which will be 1 over some number, using that as a scalar, and then multiplying it with the switched positions of the original matrix. If you want to look into the theory of mathematics in university, this is, in comparison, a walk in the park. What's there? This is very heavy theory, and it is very intimidating to see, especially with no visual or no context. So if you come this far, well done. We'll look into an example and see how we can do this. Just remember that there's always going to be an easy side to this by using your calculator, which I just showed. All right, let's have a look. We're going to find the determinant for both of the following matrices, for A and for B. We're going to see if the matrices are singular, and we're going to explain why. And then, if possible, we're going to see if we can calculate the inverse based on if the matrix is singular or not. Okie dokie, how do we tackle this? So matrix A, in the first example, is 6, 3, 2, 2. All right, we're gonna find the determinant. To get the determinant, we are just going to get A and D and multiply it together and take away 3 multiplied by 2. So remember, this was A, B, C, and D based on that matrix there. 6 times 2 is 12, and 3 times 2 is 6, giving me the answer of 6. So the determinant in this case is 6. This is a non-zero answer, so to answer C, are the matrices singular? Well, in this case, this matrix is not singular, as the determinant of that matrix is 6, which is a non-zero number. This means we can actually find its inverse. All right, let's find the inverse. So D, the inverse, is just using that original formula here, 1 over the determinant, which we already found. It's 6. The determinant is 6. So it's 1 over 6. Open up your matrix. We're going to get a matrix for the matrix A and D. So the numbers within the position A and D are going to be swapped around. So that is 6 and 2. So now 2 will be here and 6 will be here. And B and C will be the same. That will just have a negative. So it's -3 and -2. There's your inverse. Now we can go one step further to try to figure this out. We can multiply the scalar with what numbers there are within here. So 1/6 times 2 is 2/6, which is just 1/3. You can use a calculator to simplify that. -3 over 6 is just -half. Same thing, but it's a negative, 1 over 3, and 6 over 6 becomes 1. That is my inverse. I'm actually not going to leave it in decimal form because this 1 over 3 becomes a recurring decimal, so we can just leave it as this, or we can leave it as this. If the fraction is a tricky fraction to use as a scalar, you don't need to worry about multiplying it in there. All this means is if we get 6322 and multiply by 1/3, -half, -1/3, and 1, we end up with the answer of 1001, the identity matrix. Such a lot of work for a little payoff, a little arbitrary payoff. The math side is pretty simple. It is confusing to understand, to say the very least, but it's very simple as long as I'm following the template. All right, we're going to do it with our last example, B, and then I'm going to wrap this one up. So B is 4, 8, and 3, 6. Now I automatically know that this determinant is going to be 0. I can tell straight away because of the visual side of what's going on. So determinant of, let's see if we can use that, there we go, nice, is 4 times 6 minus 8 times 3 times 3, which is 24 minus 24, which is 0. So we can't determine the inverse because this here, it is singular. It is singular. As the determinant, the ET of B, is equal to 0. Therefore, inverse cannot be found. In other words, there isn't a matrix that we can multiply this with to get the answer 1001. It is impossible. And the reason why is because when you plug 0 into the formula for the determinant, you can't work out what 1 divided by 0 is because this is undefined in the maths world. This is undefined, and this kind of just breaks maths, as some students say. Right, that concludes this video. A lot to take in, a lot to digest, but there is a purpose for this, which will be used in the next lesson, last lesson. Until then, check your log sheet, see which questions you need to do, and I'll see you in the next video. Bye.